Good morning, students.
Good morning, sir.
Yes, students. Then our chapter that elasticity is over. Yesterday I sent you one worksheet. Right. Complete that worksheet and all the problems that you have from any book that you are doing. Okay. On Saturday, we'll discuss those problems. All right. So finish all the things which are there in elasticity. Saturday, we want to finish it. Right. Today, we are going to start a new chapter called SHM, Simple Harmonic Motion. Okay. Simple harmonic motion. SHM. Right. So what is simple harmonic motion? First thing that we know about simple harmonic motion is it's periodic. Okay, it's a periodic motion. And the question comes out, what is periodic motion? What is periodic motion? Periodic motion means is a motion which repeats itself after a certain interval of time or after a period of time. Okay, a motion that repeats itself. That repeats itself after an interval of time. Example, circular motion. If you keep on doing, if you have, suppose a stone is there and you are rotating it, okay, it's a periodic motion. So we can say, or if suppose we not circular motion of what we are doing, then we can say that arbitrary motion of planets around the sun or motion of electron around the nucleus. These are all examples of circular motion. Okay. Example, circular motion of electrons around nucleus or motion of planets around the sun. Okay, this is periodic motion. What else? Then it says it's a to and fro motion. What is simple harmonic motion? It's a to and fro motion. Okay, fine. It's to and fro. Okay, it's about mean position. There is a mean position, goes that side, comes back and goes that side. And then we call it as simple harmonic motion. So it's called to and fro motion. That means it oscillates. Now, oscillation and SHM both are same thing only. Okay, this you can call as oscillation also. It oscillates about mean position. Now, in this one, mean position is there. Now, what is mean position? Mean position means equilibrium position. Okay, this mean position is equilibrium position. Okay. So this is what we know about simple harmonic motion. It's periodic motion, it's to and fro motion. Okay, note that. And here one more thing you add. In this one, I didn't add SHM. SHM is also periodic, okay? This example is SHM also. Completed?
Yes, sir.
Okay, everybody?
Yes, sir. Yes.
Right.
Yes, sir.
Right. So SHM is periodic. SHM is to and fro. That means it's very simple that the motion of the planets around the sun is not simple harmonic. Okay. Motion of electrons around the nucleus is not SHM. They are periodic, no doubt about, but they are not SHM because SHM has to be periodic also and it has to be to and fro also. Okay. Let's see one more thing if we can say, or let me frame one question. So suppose that we have a ball. There is an elastic ball we have. There is an elastic ball. Okay. And we are going to release it from some height. This is ground. Okay. We have elastic ball. There is elastic ball here. We are releasing it from height h. Released. Okay. It goes, strike the ground, goes again back to height h. Okay. Keeps on bouncing it on ground. Right. So is it elastic motion or not? Or rather, SHM or not? An elastic ball is released from height h. After striking the ground. It again goes back to height h. Like this, it keeps bouncing. Like this, it keeps bouncing. Is it SHM? That is the question from you. Is it SHM or not SHM? Noted question? If you have noted, then I will ask you. Yes, Dhanya, what is the answer? Is it SHM or not? Dhanya? Respond, tell me yes or no first. Some problem is there with Dhanya. Vidya, what's your answer? My God, nobody is responding. Am I audible to you? Are you getting my voice?
Yes, sir.
Yes,
Okay.
sir.
Okay. So Vidya is not responding. Danya is not responding. Okay, let me ask then from Vaibhav.
Sir, it is not SHM.
It is not SHM. Okay,
Yes.
not SHM. All right. One answer is there, it's saying not SHM. Okay, Madhu. Madhu is there? No. Shweta, what's your answer?
So it is a SHM, sir.
It is SHM. Okay. Akhilesh?
Sir,
Not getting Akhilesh. Say again.
SHM.
SHM. Okay. Ashini?
So it is not an SHM.
Not SHM. Okay. Shweta? Shweta already said. Okay,
Yes, sir.
fine. Srinidhi?
Sir, it is not HSM, sir.
It is not SHM. Okay. Now, what my answer is? My answer is it's not SHM. This is correct. Why? Reason is because you need to do to and fro, correct? This is, but to and fro about what? There should be some point about which you need to go to and fro. Here, which point? Is this point we can say to and fro? No, to and fro is not like this. To and fro is, if suppose I say that this is mean position, then to and fro is this side also and this side also. Is it happening over here? About this point only, above. It's not coming down. Okay, so this type of to and fro motion is not required. Okay, this we can say by judging itself. What are the other conditions under which we say that it's SHM or not? That's different. But at the moment, we can clearly say that there is no fixed point about which it's moving to and fro. To and fro is like this. So it's not SHM. Okay. Later on, we will see that, okay, its acceleration is constant throughout. It is G only. So that's why it's not SHM. That we will see later. But at the moment, it's not to and fro. That's why it's not SHM. Okay. It's not to and fro. Okay, note this one. Note it first. Completed? Is it over, students?
Yes, sir.
Yes.
Okay.
Yes, sir.
Right. Now, one more question I'll give you. Let's see this time what you say. So this time it is something like this. Okay. There's a smooth slide. Smooth slide. Okay. And I am releasing one block from here. Okay. Same angle. This angle here and this angle here are exactly same. We're releasing from here. Released. Now, This comes over here, goes that side, then comes here, goes this side, keeps on oscillating. Keeps on oscillating. The block after release keep oscillating. Is it SHM? Noted question, students?
1 minute.
Now who is going to tell me? Shaktidharan?
Sir, it is the SHM, sir.
Okay, it's SHM. Okay, Madhu?
Sir, it is SHM, sir.
It's SHM. Okay. Vidya?
It is SSM, sir.
HSM. It's not HSM, SHM. Okay. Okay, fine. Right. Then who shall I ask? Vaibhav?
Sir, it is SHM.
It is SHM. Okay, my answer. It's still not SHM. This is the answer. Why now? Looks like there is this position, it's going this side also, that side also. To and fro is there, 100%. But then in this, there is one problem. What? It's acceleration. I know its acceleration is g sine theta. Throughout g sine theta? Yes. That is the problem. When it goes this side also, then also retardation is again g sine. So that means it's a constant accelerated motion. From here to here, constant acceleration, here to here, constant retardation, again constant acceleration, again constant retardation. Acceleration is having same value throughout. So it's not SHM. In SHM, acceleration keeps on changing. Okay? Acceleration need to change every time. Every moment, acceleration is different. Okay? So what it is? I said it's not SHM. Reason is what? In SHM. But is it oscillation? Yes, it's oscillation. Yes. SHM is also oscillation, but SHM is a special oscillation. Okay. So what it is? In SHM, acceleration keeps changing every moment. Every moment. But here, in this case, but in shown case, acceleration is constant. Hence, it is oscillation. I said oscillating, yeah. So no need to write again. Okay. In SHM, acceleration keeps changing every moment. But in this one, it is constant. That's why it is not SHM. Okay, that's why it is not SHM. Okay, that's why it is not SHM. Understood that?
Yes, sir.
Okay. Fine. What SHM is? We don't know yet. Okay. First note it, then I'll tell you what SHM is exactly. Completed, everyone?
Yes, sir.
Okay.
Yes,
Okay. So let's understand now kinematics of SHM. What is kinematics? Motion. Nothing else. Okay. Just a technical word. Kinematics of SHM. Okay. First thing is understanding is very important. What this motion is. Okay. So what we'll do is we'll derive it from circular motion. Okay. We'll derive it from circular motion. Why circular motion? Because circular motion is periodic and SHM is also periodic. That's why we'll derive it from circular motion. So then why circular motion? Some other motion is also possible. Reason is because circular motion we know about. We know about circular motion. We have studied about it. Okay, that's why we are taking circular motion over here. So let's see. Circular motion. Let's make a circle then first. Okay, here is a circle. And then let's make one particle in this one, which is moving continuously. Okay. So first of all, radius. What radius shall we take? R. Okay, R is the radius. And then we have to take one particle also. So first, before that, let's make one, both diameters of this. Both diameters we'll be making. It's diameter number 1. Okay, and then diameter number 2 also we want. Diameter number 2. Okay, and this is diameter number 2. Both diameters we make. Okay, now we have to take one particle which do simple harmonic motion. So from where shall we take? Okay, let's take it from here only. It starts from here. This point I am saying is O, and this is our starting point. Let's say A. Okay, the particle is at A and it's going to start its circular motion. So it's starting with angular velocity of omega. Starts with an angular velocity of omega. Okay. After some time, after time t, this is our particle. Reach point B. Okay, it reached point B. So it's here, let's reached over here at point B. So the question is, how much angular displacement is there for the particle? Angular displacement means what angle? It reached B, then what is this angle? So angular displacement of particle what it will be? Speed is omega, time is t, so theta will be omega t. What else? This will be omega t. Why? Is omega constant? Yes, omega is constant. Did I say any acceleration is there? No. Omega is constant. Right then. Omega is constant. This particle, nowhere I have written. Particle performs circular motion with constant omega. Okay. So theta equal to, what the formula is? Theta equal to omega initial into t plus half alpha t square. But alpha is not there. So theta equal to omega t. That's it. You written. So this angle is theta, which is equal to omega. Fine. No problem. Right. But where is SHM? This is circular motion only. So what we say is, if suppose we are going to project its shadow, this particle is there, its shadow, if I am going to project on any of the diameter, okay, whether it's along x-axis or along y-axis. If the shadow of this particle, which is performing circular motion, we are going to take it on this diameter or on this diameter, that shadow does simple harmonic. Okay. What it is, I'm writing it again. The projection of shadows, projection of particle performing uniform circular motion. Performing uniform circular motion on any of diameter of circle is SHM. Now we have to understand that. This is the statement. Okay, what is SHM? This particle which is performing circular motion, its projection on, we are going to see y-axis at the moment. Okay. So its projection on this diameter, which is represented by y-axis, is doing SHM. Let's see. Okay, let's see. So first of all, this shadow. Now shadow means what I'll do is, wherever this particle is, we are going to put a torch over here. Let's put a torch. Okay, what this torch is doing? It's going to put light over this one, and this point, if this is a particle, then there will be a shadow forming on this. Okay, so let's see. Where is the shadow? Just check now. Suppose particle is here and I am putting the torch here. So where will be the shadow? Shadow will come here only. On this diameter, the shadow is here. This is the shadow. This particle shadow here. Okay. When the particle reached over here, you are putting the light from here. Where will be the shadow? Shadow will be here. Okay. Then let's see particle reach further. Let's put the points. This is particle. Then particle comes here. Then maybe particle comes here. Then particle will come here. Then it will be here. Then it's here. And then again here. Well, let's see. Where are the shadows? Shadows is forming at which point? Now when it's here, you are putting torch from here. So where will be shadow? Here. When it comes this side, now torch will be from this side, not from that side only. Okay. The torch always is from the behind, from here. Here is your torch. Okay. This is the torch here. So then where will be the shadow? Shadow will be here. When you are coming over here, then it's shadow here. When you are here, then shadow here. When you are here, it's at this point. Then again you reach over here. So again torch is here. So then it's here. And again back. That means here. So see, when the particle is over here, its shadow is this point. I'll show you. See now. When particle's circle is over here, its shadow is here. When it goes up, see, both fingers you have to check at the same time. Okay. See, this is going to do circular motion this hand, and this is going to do SHM. Now check that. Okay. Then this is going that side. Right? Okay. Shadow is doing like this. And this is doing circular motion like this. Is that point clear? Is it clear? Are you able to understand?
Yes,
So
sir.
why
Yes.
I am saying circular motion, I can clearly say that circular motion is the primary motion from which the SHM is understood. You can understand it from circular motion only. Without circular motion, if you try to understand SHM, you will be in big trouble. Okay, so circular motion is the reference. That's why I've written kinematics of SHM. Okay, So circular motion is the motion from which we can understand simple harmonic motion. So circular motion a particle is doing, that particle's projection on the diameter. You can choose any diameter along x-axis, y-axis, or in between somewhere, anything. But we are choosing y because it's easy for us. Okay. So it's projection on what we have written, projection of particle performing uniform circular motion on any of diameter of circle is this. Okay. First you note, make the diagram, then we will try and find out the mathematical equations from here. Okay. Note it. Completed? Completed, students?
Yes, sir. Yes, sir.
Yes, sir.
Good. Okay. So let's see again one more time. I'm making the same diagram instead of deleting that over there. So circle for us. Okay. Diameters. Okay. One more. Right. This point is, we said O. Radius is R. Okay. Now, what I'm going to do is, initial position of the particle I'm not taking here. I'm saying initial position of the particle is here. This is initial position. Okay. Initial position is this. That is theta. Not omega t. This is theta. Okay. And the particle is moving with angular velocity omega 1. In time t, particle moves to point B. Moves to point B. So it's here somewhere. Okay, we'll reach to point B. But before that, we are going to talk about point A only. Okay. So if the particle which is doing circular motion is at point A, where is its projection? On y-axis. It's here. This is projection. Right? Now, what is its position? From mean position. Now, where is mean position here? This is mean position. Okay. Mean position is center. So everything we measure from mean position in SHM. Okay, it's kind of origin for us. Okay, everything we'll measure from mean position. So we want to know what is this position of particle A. This, I would say this is YA. What is YA? I should be finding. Now see, this is YA. Now this is equal to this. This is also Y only. That means at least magnitude wise. Whatever is this, same as this. Okay. Now this is R. So I can say YA is basically R sine theta. YA is R sine theta, which is initial position for our projection point. Okay, this is initial position. Then what has happened? From A it went to B. Okay, let's join this one also. From center, it's like this. Okay, what is this angle? We know this angle is omega. This angle is omega t. We know in time t, particle moves to point B, then angle traverses omega t. Now, I want to write YB also. Okay, let's see YB. Now, YB is what? Projection from here to here. Now, this is YB, this one. Okay, so from here again you drop perpendicular over here. Then what we will be writing YB? See, I'm writing. YB will be R sine omega t plus theta. Y equal to R sine omega t plus theta. Okay. Now in this equation, in this YB, what is theta? Theta is called initial angular position, or theta is called initial phase. Remember that these are the terms we use in SHM. Theta is what actually initial angular position of particle doing circular motion. But in SHM, we call it as phase. Okay. So theta is initial phase of the particle. And this total omega t plus theta is phase of the particle at time t. Okay. This omega t plus theta. What exactly it is for circular motion particle? Angular displacement of the particle or angular position of the particle after time t. But here what we are saying? Phase. Okay. Phase of the particle at time t. Okay, fine. No issues. Now let's say that this reached to point C. Where is point C now? Point C is right at the top. Here, that's point C. Right at the top. Now, if I have to find position YC, YC will be what? YC will be equal to R. Right? So YC equal to R only. What you can do in that? Angle traverse is 90 degrees. From here, it has traveled 90 degrees. Theta plus omega t plus some more angle, whatever that is, that's equal to 90. We know that. So at point C, I can see that YC basically is equal to R. Is it the maximum value of displacement of the particle, this projected particle? Yes. From here, it will come down. Okay. So this is maximum displacement of the particle from mean position. Maximum displacement of projection. Maximum displacement of projection from mean position. So we call it as amplitude. Okay, what we are calling is amplitude. Not that's why. This is called not like this. again. This is called amplitude. Okay, so since it's called amplitude, this is replaced by A. Because we write amplitude with A. So R has become A. Okay, so if R has become A, that means this YB, now I'll be writing as what? YB I'll be writing as A sine omega t plus theta. So if suppose I am going to write this one at some other time, T1, T2, T3, T4, and I say you write the position. What is going to change in that? Is theta going to change? No. Its initial position, how can it change? Is A going to change? No. Only T is going to change. So position of the particle at any time, A sine omega, that time plus theta. Okay. So what we'll write? Position of particle. Position of particle at any time T is written as what? Y equal to A sine omega t plus theta. That's all. Why? Because we know that if you are talking about circular motion also, what will be the angular position of particle? Omega into t, whatever time you say, 1 second, 2 second, 4 second, 5 second, 8 seconds. Accordingly, it will be traveling angle. So exactly same way in SHM also, the position will be given by A sine omega t plus theta. So this is how we find the position of any particle. Okay, very important. Okay, position of particle doing SHM from mean position. Very important. Position of particle doing SHM from mean position. Tell me, is everything clear? Any doubt? Any doubt to anyone? Students, don't sleep. Say yes or no.
No, sir.
Okay, note that. Completed? Completed, students?
Yes, sir.
Yes, sir.
Okay. So now we got this is the position of the particle at any time t with initial phase theta. Now, is this only the form or there can be another form? Can there be cos also? Cos also possible. When I am going to see its projection along x-axis. Suppose at point A, then torch will be here. Okay, torch is here this side. Then projection will be here. Then the position will be like this. So this position will be what? Cos. It will be a cos theta or r cos theta, whatever you say that. Then it can be written in terms of a cos omega t plus theta also. Okay, on any other axis or an x-axis, if we are having the same thing, would have been written as x equal to a cos omega t plus theta. So sometimes when the question writes this as equation of SHM, don't get surprised. You can write, okay, along x-axis. Along x-axis, same equation we can write like this also. Okay, so don't be surprised or don't panic or what it is. We studied only sine theta, how cos. This can also be done. And remember that when we're writing this as simple harmonic motion, this harmonic basically means what? Harmonic means is an equation which is represented by harmonic functions, and sine theta and cos theta are harmonic functions. They keep repeating itself. That's why they call harmonic functions. Okay, so that's why this equation is also represented in terms of sine theta also and in terms of cos theta also. Both are harmonic functions. Okay, so this as well as this. But what we are going to use? We'll solve everything with this. Okay, right. But if cos is given, if the question cos is given, then we will solve that also. Okay, we will solve that also, no problem. Note it. Note this x equal to a cos omega t plus theta also. Done? Completed?
Yes, sir.
Okay.
Yes, sir.
Right. So we got position of the particle. Okay. Position of particle performing SHM. We are writing it as y equal to a sine of omega t plus theta. Fine. What about velocity? This is position. Velocity of particle. Performing SHM. Velocity means what? The rate of change of position on dy by dt. What else? Dy by dt. So what is going to come? So a is as it is, it's a constant. Sine's differentiation is cos. Then differentiation of this thing. The differentiation of omega t. Omega is constant, differentiation of t with respect to t, 1. Then differentiation of theta. Theta is what? Is it changing? No. It's initial phase. So it's constant. So constant differentiation, 0. So what's going to come? Only omega. So I got velocity of particle as a omega cos omega t plus theta. V is a omega cos omega t plus theta. So okay, fine. But this is one form. Okay, this is one form. Another form also I want to get. What is that? This cos I don't like. I want to convert this into sine only. Okay, so what I'll do? V equal to omega. Inside is a cos omega t plus theta. So this a cos omega t plus theta I am writing root over 1 minus, or a you take outside only. Later on we'll talk about it. 1 minus sine square omega t plus theta. Okay, 1 minus sine square omega t plus theta. Then what we can do? See, V equal to omega, this a I am taking inside, root over. When this a goes inside square root, it becomes a square. A square minus a sine omega t plus theta whole square. When this goes, this becomes a square sine square omega t plus theta. A square sine square omega t plus theta I am writing as a sine of omega t plus theta whole square. But a sine of omega t plus theta is what? Y. So V value omega root over a square minus y square. This is another form of V. This is one form. This is another form. Are these formulas? Yes, these are formulas. So y equal to a sine omega t plus theta, v equal to a omega cos omega t plus theta, or v equal to omega root over a square minus y square. Okay, now more. What is the maximum value of y? Maximum value of y is a, amplitude. Okay. Maximum value of y is a, which is called amplitude. Maximum value of v, maximum value of v is a omega, because this will become 1. Here also same, no? When it was maximum, sine omega t plus theta became 1. That's why y equal to ak. Same way, when we want velocity maximum, this cos omega t plus theta will become 1, v equal to a omega. But how is that possible that this and this become maximum at the same time? They will not become maximum at the same time. Velocity will be maximum at some other time. Position will be maximum at some other time. In fact, when position is maximum, velocity is 0. Okay, when position is maximum, velocity is 0. That we will see. Okay, but right now, what is velocity maximum? So velocity maximum is v is maximum when this becomes 1. And what is its value? V maximum is a omega. And when V maximum? When y is 0. You can see, when y is 0, then only it will become a omega. Okay, and when y is a, if you are going to put over here a, then we will become 0. Okay, so V maximum is a omega. You can write that, and V minimum also if you want to write 0. When? That also you write. When y is equal to a. And this is when y equal to 0. Note that Completed?
Yes, sir.
Everybody?
Yes, sir.
Yes,
sir.
Yes,
Okay.
sir.
Right. So position we know, velocity we know. Let's go for the acceleration. As I told you that last time around, acceleration is not constant in SHM. Let's see. So acceleration. Now, acceleration is what actually? Acceleration actually dv by d. And what is v? We saw v was a omega cos omega t plus theta. This is what we saw v as. Okay, to differentiate that. Now a is amplitude, that's constant, omega is constant. Now what to differentiate? Cos omega t plus theta. The cos differentiation is minus sign. So minus of sine omega t plus theta. Then differentiation of this. The differentiation of this is omega. T's differentiation is 1, theta's differentiation 0. So only omega. Now what we have? Minus a omega square sine omega t plus theta. So see then, with the time, is sine value is going to change? Yes. So acceleration also is going to change. Okay. This is one form of acceleration. Then what is the other form? Other form is acceleration equal to minus omega square a sine omega t plus theta. And this is y. This is y, position. So acceleration is minus omega square y. Okay, it means acceleration will always be in opposite direction to displacement or position. So if this is our mean position, okay, and the particle is here, this is y, then where is acceleration? Acceleration is acting like this. It's minus omega square y. If suppose particle is here, then where will be acceleration? Here. Why? Because position is negative. Y value is negative. So acceleration will be like this. So here acceleration is towards mean position. Here acceleration is towards mean position. What does that mean? Acceleration always act towards mean position. Very, very important point. Okay. Acceleration always act towards mean position. Acceleration is always towards mean position. Okay, when particle is having positive y, it is acting downwards. When particle is having negative y, it is acting upwards. That means its direction is always towards mean position. Okay, note that this is about acceleration. Completed?
Yes.
Okay. So acceleration always x towards mean position, very, very important point, and that is the condition of SHM as well. Okay. Acceleration need to be always towards mean position, and it is equal to omega square y minus omega square y. So they say that condition of SHM. What is the condition of SHM? Acceleration need to be negative of y or negative of position of the particle. This is condition of SHM. Okay, we already have got acceleration equal to minus omega square y. Okay, so what is equation of SHM? Equation of SHM is this acceleration they write as d square y by dt square. That means double differentiation of displacement. That's what we did. First, this differentiation, not displacement. Double differentiation of displacement. First, when we differentiated displacement, we got velocity. Then again, we differentiated, we got acceleration. Okay. So acceleration place, we are writing d square y by dt square. And this omega square will bring it over here. This is equation of SHM. Okay, note that. It's important. This is important. And this anyhow is a formula, you know that. Okay. Note it. Completed?
Yes, sir.
Okay.
Yes, sir.
Now let's make graphs. Okay. We will study graphs. Graphs between what? Graphs between first position and time. YT graph. This is Y and this is T. And what is the relation? Relation is Y equal to A sine omega T. I'm not writing theta. So if I'm not writing theta means what is theta value? Theta value is 0. Okay. Theta is 0. That means initial position of particle is mean position. Okay, it's starting from mean position only. That's why theta is 0. That is the meaning of that. We can see that if t equal to 0, what is y? 0. Okay, if t equal to 0, then what is y value? 0. That means it's starting from mean position. Right. So this I want to plot here. So this basically is what sine function. And how sine functions graph used to be, same graph we are going to make here. So graph is like this. Initially 0, y value 0. It starts like this. This is a sine function. This is sine function. In this one, what is this? Maximum value, that is A. Here also, this is maximum on the other side. So we can say minus A. Okay. This maximum value, when we are going to reach? When time is how much? Let's see. When this y will be maximum? When this sine omega t will be 1. That means omega t will be 90. Okay. Omega t will be 90. That means omega t pi by 2. Okay. And what is this omega? Omega we used to write it as 2 pi by time period into t equal to pi by 2. So what we are getting? See, t is coming t by 4. So after 1/4 of the time period, that means here I can write t by 4. See what I am doing. This is very important for us. Omega t equal to pi by 2. This value need to be 1. This value need to be 1 means this angle need to be 90. That means omega t is pi by 2. What is omega? Angular velocity. 2 pi by t, 2 pi by time period. This t is what? Time period. T is time period. What is time period? Time to complete one circular motion, because ultimately it came from circular motion. Time to complete one circular motion, or in this one, time to complete one oscillation, one to and fro motion. Okay, both are same. So t is time period. So 2 pi by t into t came t by 4. See next one. This is again becoming 0. Who? Y. Again 0. This should be 0 again. But this value is not 0 this time, because you already have moved. You started from 0. How can you come back to 0? No. Theta 0. Now it will be again 0 when you have rotated by 180 degrees, when you have traveled 180 degrees. So when you, this is 180, this y will become 0 again. So that means again what? Omega t equal to pi. Again, 2 pi by t into t equal to pi. Pi cancel. Again, t equal to what? T by 2. And this is t by 2. So see that every quarter of the time period, 1 maximum amplitude, 0 amplitude, and then this one, this is minus a. When it will happen? 3t by 4. Next quarter of the time period. And this again, t. So this is one oscillation of the particle doing SHM. 0, a, 0, minus a, 0. This is the position. This is called YT graph. Is that clear? Any doubt? Any doubt, students?
Yes,
Okay. Okay. Noted. Done?
yes,
Okay. So this is your YT graph. Then VT graph. After this, we'll make VT graph now. Let's see. So V is what now? Y equal to A sin omega t. So V equal to A omega cos omega t. V equal to A omega cos omega t. Here only we'll be making. Okay, this is V and this is T. Now this is cost curve. Okay, so when this is 0 over here, velocity is maximum, because we said that velocity is maximum when y is 0. So we'll take it from here. So just for the reference purpose, just extend this one so that it looks like we have made in a proper way. Okay, let's try. It is like this. Like this it is. Okay, now this value is what? This value is A omega. And this value here, minus A omega. This time, T by 4. This time, T by 2. This time, 3T by 4. And this again, T. Okay, this is cost curve. So you can see over here, when position is 0, velocity is maximum. When position is maximum, velocity is 0. Then again, when position 0, velocity is again maximum in opposite side. When velocity is 0 here, position is maximum. So they have 90-degree phase difference. What is the angle difference between them? 90 degrees. So we'll write over here, V and Y have 90-degree phase difference. -90-degree phase difference. Or you can say V is ahead by pi by 2 radian from Y. If we are going to compare this function and this function, that cos omega t, I can write this as sine of 90 plus omega t, or omega t plus 90. Omega t plus sine omega t plus 90 is what? Cos omega t. So if we compare this and this function, we say that V is 90-degree ahead of Y. Okay, V is 90-degree ahead of Y. So that's what I have written. V and Y have 90-degree phase difference first, right? V is ahead of pi by 2 radian from Y. Remember that. Okay, note that one also. Make the diagram. If doubt is there, ask. Any doubt is there, ask. Completed? Students completed?
Yes.
Yes, sir.
Yes, sir.
Okay. I think time is over. Okay, we'll finish it here today. Then we'll see more graphs. 2 more graphs are there. Rather, 3 more graphs are there that we have to make. So I won't be able to make it. It will be too late. Okay. So we'll finish it over here. On Saturday, possibly after discussing the worksheet and your doubts, we'll complete this. Okay. Right then, students. See you in next class. Bye-bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir. Thank you.